Atoms are the smallest units of matter that still retain the identity of an element, yet inside them exists a surprisingly rich and dynamic world. At the heart of every atom lies the nucleus, a dense core made of protons and neutrons holding almost all the atom's mass. Surrounding this nucleus is a vast region of space where electrons exist, moving according to precise physical rules. These electrons are not scattered randomly. Instead, they occupy specific energy levels, known as electron shells. Understanding these shells is essential to understanding chemistry, physics, technology, and even life itself, because the behavior of electrons determines how atoms bond, react, emit light, and store energy. The concept of electron shells developed gradually as scientists tried to explain why atoms behave the way they do. Early atomic models imagined electrons orbiting the nucleus like planets around the sun. While modern quantum mechanics has refined this picture, the shell model remains a powerful and intuitive way to understand atomic structure. Each shell represents a specific energy level, and electrons can only exist in these allowed levels, never in between. When an electron moves from one shell to another, it must absorb or release a precise amount of energy, a rule that explains phenomena ranging from chemical reactions to the colors of fireworks and stars. The innermost electron shell is called the K-shell. It is the closest shell to the nucleus, and therefore experiences the strongest attractive force from the positively charged protons. Because of this strong attraction, electrons in the K-shell have the lowest energy of all electrons in the atom. The K-shell can hold a maximum of 2 electrons, and when it is filled, it forms a very stable configuration. In fact, many of the most stable elements in nature owe their stability to the complete filling of their inner shells, starting with the K-shell. Moving outward from the nucleus, the next energy level is the L-shell. This shell is farther from the nucleus than the K-shell, and therefore has a higher energy. The L-shell can hold up to 8 electrons. These electrons are still strongly influenced by the nucleus, but slightly less so than those in the K-shell. As atoms become heavier and contain more electrons, the L-shell fills after the K-shell is complete. The filling of the L-shell plays a crucial role in determining the size of the atom and the way it interacts with other atoms. Beyond the L-shell lies the M-shell, which can hold up to 18 electrons. At this distance from the nucleus, the attractive force is weaker, and electrons have significantly higher energy. The M-shell is especially important in transition metals, where electrons in this shell contribute to properties such as magnetism, electrical conductivity, and color. The complexity of the M-shell is one reason why transition metals show such a wide range of chemical behaviors compared to simpler elements. As we continue outward, we encounter the N-shell, capable of holding up to 32 electrons. This shell is found in heavier elements and plays a key role in determining their chemical reactivity. In many atoms, the outermost shell, often the N-shell or beyond, is known as the valence shell. Electrons in the valence shell are the most important for chemistry because they are the ones that participate directly in bonding. Whether an atom forms strong bonds, weak bonds, or no bonds at all depends largely on how many electrons occupy its valence shell. Beyond the N shell are the O, P, and Q shells, which appear in very heavy elements. These shells follow the same basic rules as the inner shells, but exist at much higher energy levels and greater distances from the nucleus. While these outer shells are less commonly discussed in basic chemistry, they are vital in advanced physics and nuclear chemistry. Elements with electrons in these shells often show unusual and sometimes unstable behavior, including radioactivity. One of the most elegant rules governing electron shells is the 2n² rule, where n represents the shell number. According to this rule, the maximum number of electrons that a shell can hold is given by 2 times the square of its shell number. For example, the K shell, where n equals 1, can hold 2 electrons. The L shell, with n equal to 2, can hold 8 electrons. The M shell can hold 18, and the N shell can hold 32. This simple mathematical relationship reveals the deep connection between atomic structure and fundamental physical laws. While the shell model provides a clear framework, modern quantum mechanics adds more detail by introducing the concept of orbitals. Orbitals are regions of space within a shell where electrons are most likely to be found. Each shell contains subshells and orbitals of different shapes, such as spherical s orbitals and dumbbell-shaped p orbitals. However, even with this added complexity, the shell concept remains useful because it captures the overall energy organization of electrons in an atom. Electron shells are not static structures. They are dynamic and responsive to energy changes. When an atom absorbs energy, such as from heat or light, an electron can jump from a lower energy shell to a higher energy shell. This process is called excitation. Conversely, when an excited electron falls back to a lower energy shell, it releases energy in the form of light. This emitted light has a specific wavelength, producing characteristic spectral lines that act like fingerprints for each element. These spectral fingerprints are incredibly important in science. Astronomers use them to determine the composition of stars and galaxies millions of light-years away. By analyzing the light emitted or absorbed by distant objects, scientists can identify which elements are present and even infer temperature and motion. All of this information comes from understanding how electrons move between shells. In chemistry, electron shells explain why elements form bonds in specific ways. Atoms tend to seek stability by filling their valence shells, often by sharing or transferring electrons. This desire for a full valence shell drives chemical reactions and leads to the formation of molecules. For example, sodium has 1 electron in its outer shell, while chlorine has 7. By transferring 1 electron from sodium to chlorine, both atoms achieve stable configurations, forming sodium chloride. The periodic table itself is organized according to electron shell structure. Elements in the same column or group have the same number of valence electrons, which is why they exhibit similar chemical properties. Noble gases, found in the far right column, have completely filled valence shells, making them exceptionally stable and largely unreactive. This stability is a direct consequence of electron shell configuration. Electron shells also play a central role in modern technology. Semiconductors, which form the basis of computers and smartphones, rely on the controlled movement of electrons between energy levels. By manipulating electron shells through doping and electric fields, engineers can create materials with precisely tailored electrical properties. Lasers, LEDs, and solar cells all depend on controlled electron transitions between shells. In nuclear physics, while electron shells are separate from the nucleus, they still influence nuclear behavior indirectly. Changes in electron configuration can affect how atoms interact with radiation and how they undergo certain types of decay. In medical imaging and radiation therapy, understanding electron energy levels helps scientists design safer and more effective technologies. The study of electron shells also bridges the gap between classical and quantum physics. While early models treated electrons like tiny planets, quantum theory revealed that electrons behave both as particles and waves. Shells, therefore, are not rigid paths, but probability-based regions defined by mathematical equations. This dual nature challenges our intuition, but also enriches our understanding of reality at its most fundamental level. From an educational perspective, electron shells provide a gateway into the world of atomic physics. They offer a structured way to introduce complex ideas such as energy quantization, wave-particle duality, and chemical bonding. By mastering the shell model, students gain a foundation that supports further study in chemistry, physics, materials science, and engineering. Even in everyday life, the effects of electron shells are everywhere. The colors we see, the electricity that powers our homes, the strength of materials, and the reactions inside our bodies all trace back to electron behavior. Photosynthesis, for example, begins with electrons absorbing light energy and moving to higher energy states, setting off a chain of reactions that sustain life on Earth.
As science advances, our understanding of electron shells continues to deepen. High-energy experiments and advanced simulations reveal subtle effects that go beyond simple models, yet the core idea remains unchanged. Electrons occupy discrete energy levels, and these levels shape the structure and behavior of matter. This enduring concept stands as one of the great achievements of modern science. In conclusion, electron shells are far more than abstract ideas confined to textbooks. They are the hidden architecture of the atomic world, governing the behavior of elements and enabling the complexity of the universe. From the smallest atom to the largest star, the rules of electron shells apply universally, linking the microscopic and macroscopic realms. By understanding these shells, we gain insight not only into matter itself, but into the fundamental order that underlies all of nature.